Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa ElDiwiny, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics Podcast. Hello, Professor Kim. Thanks so much for joining us in the podcast. I would like to ask you first how you'd like to introduce and define yourself for the audience who first time listening to you.
Hi, my name is Sangbae Kim. I'm a professor in mechanical engineering at MIT. I'm a roboticist. I love design and fall in love with the control of the leg robot. And I built many robots, including sticky bot, ice bro, spiny bot, mesh worm, and 4 Cheetah series, like for Cheetah and Cheetah 2, Cheetah 3, and mini Cheetah.
Yeah.
So on. So I love to talk about leg robot. I love to talk about mobile robot and application in the real world.
Wonderful. So thank you once again for joining. But we are curious to go for your childhood. How was your childhood was? Were you interested in science or technology as a kid? Do you have any memories about that?
Well, I always loved building. As many engineering students or most of kids like love Lego. That's how it started. But I think that quickly evolved to like building something more, how can I say, active. Like I love electric motor, and then building my own stuff. Lego, is limiting. Lego is very convenient, but there's a lot of limitation. Yeah. So I start building, cars by myself, and then I realized so hard. And then that's where I fell in love with the RC cars. Yeah. And RC car at the time was such a big source of learning experience because it teaches you like all kinds of vehicle dynamics and the design of the suspensions and shock absorber. Like I learned a lot of like a sort of like a physical sense through RC car before even learning simple mechanics. RC car was such a big learning experience for me. And of course, like, the gliders, then rubber powered gliders. I went to competition every year when I was a middle school student, and I loved physics. I had a Korean version of a Thinking Physics is a book you can find Amazon. It's a fantastic way to teach physics for middle school student to the adult. It teaches you intuition instead of falling the loss in the equation. So I always love physics. That's how I think. Yeah, that's pretty much it. I always cut things with the knife because I didn't have a tool. And then when I first got my electric drill when I was 13, that just changed my world.
Yeah. This is really very interesting. You're a very smart kid. So, but I'm curious about what's the actual first robot you built?
First robot I built, I probably is the something I can call robot is the Ice Pro. When I was at Stanford, they had a cockroach-inspired robotics project. They tried to learn how to simplify the model of the insect running and then replicate in the robot. And they had a robot called the Spirulina, which is a pneumatic powered machine. But they, because it's a pneumatic power, the robot cannot be completely power autonomous. So I joined the Mark Kukowski's group and start building independent, power independent machine. And then it turns out that it's Ice Pro. At the time was the fastest running robot in terms of the body length per second. Now, not really. But yeah, that was my first robot.
But I'm curious to ask you, since you are now one of the pioneers in legged robot design, and how this was a style for you? When you get an inspiration for this designing, you mentioned you were interested about physics, but we have the question: what kind of maybe abstraction you can get from, for example, MIT Cheetah robot that's 3 version now, and the mini one. So what kind of inspiration you look for replicating the motion? Or you go for something beyond what we have already in nature? How you can make this happen to make a useful design?
So the legged machine is still, how can I say, is in the middle of the evolution, in my opinion. Wheeled vehicle didn't exist in nature. Humans somehow invented it, like thousands of years ago. And then it became a thing, became proven to be very, very useful. And engineers, from, Roman era or even before, always wondering about why not we have a legged machine. They can, because we had an example in nature. Humans are a good example, and other animals are example, and then they do perform excellent job in moving around the world terrain and so on. Yet replicating animals are not easy, and as you can see, even just Cheetah series by itself, let alone all kinds of examples in robotics community, it started with a more animal-looking design, and then it get quickly simplified to be more practical. And in my opinion, I think it's still too complex to be practical. And we're still in the middle of the evolution. What can we learn from nature is still also, in the middle of the evolution. We're still not sure what inspiration is good, what inspiration is not useful. One thing I can say is the animals, biological systems are just way too complex to replicate anything. So we've been always focusing on the simplification of design and focusing on the principle. One example I can tell you that was useful is the animals' legs. If you look at the animals' legs, especially the fast ones, they have a very little mass in the leg, especially going to the distal end, that minimize the required torque on the shoulder and so on. So we focus on that for last 10 years, how to minimize the limb inertia. That really allow us to build a robot that can be very powerful and dynamic and efficient.
But I'm curious to ask you, it is very interesting experiences about what kind of elements you have to get inspiration from nature, for example, in MIT Cheetah robot. But I'm curious to ask you what could be the missing pieces here. If you can have a step back and look what's really missing, since we are still in the middle of the evolution for that. What are the missing pieces, do you think, that we have to focus on?
So there's two aspects, like a hardware aspect and software aspect. In hardware aspect, we cannot afford to have as many joint and actuator like animals. For example, dogs have 700 muscles, or cheetah has 12. It's not even close. And we always talk about how nice it would be to have ankle joint, and then it's practically impossible because our actuation technology is not quite there yet. There are a lot of complexity plus weight and robustness issue. And the fabrication challenge, I guess, like if you think about how to fabricate a paw, like a robotic paw, is very, very difficult to replicate what animal has. But I think bigger challenge is in software, much bigger challenge. We just talking about just the biology itself, we just don't even scratch the surface of how animal balance and then perform what they do, like combined with the vision and planning everything. And even though we don't completely understand how animals do, in algorithm world where optimization or machine learning is just the beginning to do a fraction of what animal is doing. So I think we're not even talking about high level intelligence, like competing with the human. We're talking about things animal like do in a second or two very easily. So low level, medium level intelligence were not even close there. So I think there's some challenges in hardware, but I think bigger challenge is because the missing part is actually the algorithm.
I think this really interesting part here about when you mention about what kind of intelligence, because we have mechanical intelligence and we have this kind of brain. So do you think in animals you are focusing more in the mechanical intelligence? Do you think which one you have to maybe give more focus, or maybe both of them? As just out of curiosity. Yeah.
To be honest, if you look how MIT Cheetah has evolved, we try to minimize the mechanical functions in the entire machine. So meaning that we just don't we try as hard as possible to minimize compliance between the actuator to the foot. Well, we have to have some compliance because you don't want hard metal leg shaft hitting the ground. So at the end effector, you need to have some compliance. But besides that, we try to minimize compliance in any mechanical play because we lose a bandwidth. That's something very often overlooked by many mechanical designers. If you don't want to have an actuator, yes, like a under actuator system, some passive compliance, mechanical intelligence do the job. That's fine. But if you want to if you want to achieve something versatile, Cheetah robot is not just running straight. If your Cheetah is running a straight and single speed, there's so many things we can do without even involving many actuator. But this robot, many mobile robot, we want to do acceleration, deceleration, turning the spot, like jumping and landing, just all kinds of behavior. We need to be able to control in every millisecond what force you want to achieve, and then the bandwidth is critical. Yeah, to be honest, it's like there's almost no mechanical intelligence in our robot, and it can be useful when you really try to minimize degree of freedom, but that minimizing degree of freedom also lead to very limited application. You can make a versatile machine. Good example is a gripper. If you make a gripper with a bunch of under actuation system, that hand cannot do many things.
Yeah, great. So maybe there's a question about what since you are already interested about designing, what could be the techniques you use for dynamic model for your robot? Because we know that modeling sometimes is super challenging, and especially when we have this kind of dynamic environment as well. But for the robot itself, the designing process, what technology do you use to create this dynamic model?
So we use very carefully designed dynamic simulation software to verify some ideas, and we do model our actuator, and we actually even use the dynamometer to test our actuator. It's all this effort to try to really model and then be accurate about what we're building. And when it comes to actually designing and making decisions, all these like tens of thousands of parameters, there's no particular method we can use here. Yeah, we basically have many hours of meetings and discussions and comparison with other machines, and where design processes are pretty much done by human discussion. Yeah, and again, you can't just have build a great machine by having great meetings. You need to have a central designer, which play the biggest role in and his experience and then concept understanding really hugely impact how the machine is designed. So designing such a complex systems are still up in the air. We don't have a good formal way to do it.
What is area or direction of research you think is very promising for legged robot, but still we maybe as a community of research we don't agree or we don't give much attention to it?
I think the locomotion algorithm or navigation algorithm. There are thousands of papers, hundreds of papers on working on navigation algorithm. But when it comes to legged robot that move around in 3D space where you have to exert forces and to choose a foot placement, this is still quite a challenging area where the typical optimization scheme, gradient-based optimization scheme, or the machine learning type of a stochastic gradient descent doesn't really work because you can't really create a cost function perfectly in every single time, and in many cases you're optimizing through multiple discrete events, which makes it very difficult to use any gradient-based approach. So often people fall into this like a mixed integer optimization, and it is very inefficient and quite challenging. So we still need to take a look at a little bit high level intelligence, like literally algorithm. Like humans are performing not in a way like we quantify everything all the time. If you just grab something on your table, we're not maximizing or minimizing value. We have a much more crude, discrete decision making process. And if you do the same task 100 times, your grasping position or force applied to the object is all over the place. They're not always consistent because we don't really care about those quantities. We care more about high-level decision, which finger I'm going to use and where I'm going to grab and what I'm going to do if slips. There's a lot of discrete decision we just don't know how to properly do. Our tools are all based on some quantity and then gradient based, like the minimizing value or maximizing value. Somebody might argue that if you throw every possible case and then make it into gigantic optimization process, it's possible, and that will require almost infinite amount of data or infinite amount of time. So we don't think that's actually quite practical way. So we have to really think about how to program a concept. We know how to program a quantity-based approach, a gradient-based approach, but we don't know how to do a concept. We don't know how to program a concept. That's basically basic challenge in everywhere in robotics, in my opinion.
That's really interesting aspect. And maybe I'm curious to ask you, what should take from us so that we can consider that in what we do? Why do you think we still don't grasp these ideas or this point? What's contributing to it?
I think just the legacy, how we do engineering is all based on mathematics, and which has a long history, 500 or more longer history. And I think we need to really start thinking about different format of intelligence, which is not easy, of course. But several people in the leadership really thought about those too. Leslie Kevling in our institute also agree with that. We really need to think about intelligence that not necessarily relying on just a quantity. At least it's not just we can't really program anything without quantity, but making decision doesn't need to be always finding maximum value or minimum value. The algorithm development should more focus on event-based reaction based algorithm, which is a lot more close to like a typical classical algorithm, like a yes and no, if or else type of. Many people call that a heuristic. I think we need to go back to heuristic and then think about how to generalize all these heuristic, which actually hugely help our robot to be more smart.
That's a good point. Yeah. Maybe I could ask you, what things you say that you highly depend on intuition as a factor since you in early ages. What's something you thought would work out very well in the version for MIT Cheetah robot, and the empirical result proved something wasn't expected, or maybe it was surprising to you, counterintuitive to you?
Well, so the biggest surprise actually it was the efficiency. We even have a paper how we make our robot efficient, but it wasn't quite planned. It's more like a aftermath. We analyze after, and it turns out that it's actually very good. because when we first designed MIT Cheetah, our goal is really run as fast as possible. We need to design a machine like a F1 Formula, a type of like concept. If robot run out of battery in 1 minute, that's still okay, because if you can run really fast, you can do so much in 1 minute. Test the fastest machine doesn't take more than a minute, even a battery. So we just completely ignore efficiency when you design the machine. We focus on force bandwidth, and then the high torque the density, and then minimum weight, and so on, like literally like a airplane design or a Formula car. And then it came out like efficiency of animal, and then it was the best in this class. I think still the best in the class, and we're quite shocked. And then it took me for at least a week to evaluate and re-verify multiple way to check our measurement is correct. We check like 2-3 different ways, and then they're all matched within like a 1% error. And it turns out that we lose so much through the transmission, which we take it as the gospel, like harmonic drive or high gear ratio system. The conventional transmission system was horribly inefficient, not only just the transmitting power, and also so inefficiency is not through just the transmission. Actually, the inefficiency happens when it collides with the object. If you look at the most robotics applications, or even a research topic, most robots are not having any impact with the object or environment. They're very, very careful in contact, because that's very hard to control. When it comes to impact, by the way, if you look any human behavior, if you watch anybody is doing any work in 1 minute, they're gonna go through like hundreds of collisions, and we don't even notice, because our bodies are so well built, and we have a nice cushions and control, so we don't really realize. We have a very we're using high-speed collision all the time. If you run, if you walk, you can do it without any collision. That's why actually most conventional robots are so slow. When it comes to collision, if your actuation have a high IMF, which is the impact mitigation factor, if you don't know what it is, Google please, because it's a very important concept in actuation. They represent the workspace mass matrix, relative mass matrix quantity. Low IMF means your machines are very rigid and then awkward to touch anything. If high IMF means you're very flexible. You can touch something and then you can control force very well. So those conventional actuation system, which is a low IMF, high gear ratio, high inertia, have a horribly inefficient in terms of the collision, because it's not you're losing energy through the transmission, you're losing by colliding with the high mass. So you lose by the impact. That eventually cause all this vibration, heat, and eventually damage all kinds of machines. So the design of the Cheetah robot, it turns out that we were focusing on high force control bandwidth, which is correct thing to do. It has a side byproduct like efficiency, and byproduct like the power generation and the power regeneration. We didn't quite plan to have a regeneration, but realize you can have a proper force control without energy regeneration. So that was the byproduct.
Yeah, that's really an excellent point. Yeah. But maybe I'm curious here, and do you think, having said that, do you think soft robotics or maybe artificial muscle could really contribute in designing these muscles for MIT Cheetah robot or legged robot in general?
The artificial muscle has always been holy grail for many engineers, and but people really need to understand that we need a different way to generate force.
Yeah.
We have if you look at the physics, there's only two kinds of way to generate force. One is electromagnetic way, which include electrostatic or electromagnetic, which is pretty much dominant. And then the other way is doing chemical reactions like boiling waters or combustions, or using compressed air type of thing. Um, but if you don't change, if you don't have any new way to generate force, just converting that kind of energy source into a different form doesn't really change anything fundamentally. So like basically, like for example, pneumatic, you can generate 1,000 different actuator with a pneumatic source, and if you cannot change how the pneumatic power conversion happen, it doesn't really help, because there's a fundamental limitation on the pneumatic power source. And combustion, same reason. Like combustion has a fundamental limitation. That's why most actuators are either electrostatic or electromagnetic. And same argument here. If you don't change how we fundamentally change how we generate electromagnetic or electrostatic, they're associated with the fundamental limitation. Electrostatic has a very different fundamental limitation compared to electromagnetic, but you have to basically tackle the basic principle, and otherwise it's going to be all ended up being same, or it cannot improve too much.
And there's a question also from the audience: what kind of maybe a limitation or upgrading for MIT Cheetah Robot version 3? What kind of advancement are you looking for, or tackling limitation you had in earlier version?
Mini Cheetah 3 is differentiated from Cheetah 2 in a way that it's more simplified. It has a more range of motion. It's designed to be much more robust. And then we also develop our own software package that has a very good model. Cheetah 2 was much more difficult to model. So we move direction, move into the much more practical or programmatic direction. So Mini Cheetah is pretty much like a combination of the design, and especially the scale is also small. It's extremely robust. We drop from like a meter height multiple times, doesn't even have any mechanical issue. Our first Mini Cheetah, we were running for like a year and a half in our lab, doing more than several hundred experiments. We didn't have a single mechanical failure. So the simple design is really, really important. I really wish the community understand that part. Like if you build a machine, sophisticated, beautiful machine, if you fail in 10 times experiment, it's not very useful. So the Mini Cheetah is sort of like hallmark of like the robust machine that can be also versatile. If you look at the military applications, the robots are extremely simple. They don't want to put more than one motor because it becomes fragile and break. And Mini Cheetah can be the first robot that actually can have the versatility and the mechanical robustness at the same time. That's going to be one of the critical design aspect in the future robot application. If robot just break, we can make a product. We can really help humanity.
That's a great point. Yeah. Here's also a question about what's your thoughts about wheels and locomotion?
So yeah, I actually thought about this a lot. And there's an inspiration from this Japanese manga, Japanese animation, like Ghost in the Shell, for example. There's a fantastic concept and so on. And I think there's going to be very how can I say, some certain area where wheeled leg can really outperform everything else. But if somebody asks like what is going to be the winner of if you consider everything, I'm still not sure, because if you have a wheeled machine, which means you have to have another actuation at the end effector. You have to move the wheel as well, and then can you get rid of some degree of freedom due to the wheel? When it comes to rope train, not really. In order to generate XYZ force properly, and you need to have all the actuator that leg robot has, and then you need to have another actuator for the wheel. It's just to make it a lot more complex. So if you want to build a robot like primarily running on the rope train, I don't think the wheeled leg robot will have any benefit. Wheeled leg robot is obviously more beneficial on the more primarily like flat train. Let's say the machine is mostly running on the flat train, maybe slightly slope, maybe a few steps of stairs. I think there's a advantage. But if the robot has to go through the rough terrain a lot of times, or you have to do both world very, very well, I still think the leggy robot without wheel is going to win because due to the complexity. It's a less complex, not having wheel.
Yeah, yeah. That's interesting aspect as well. Yeah. And also here's a question about humanoid robot, for example. Why does Boston Dynamics Atlas robot have knees like human, bend forward, while other designs sometimes bend backward? And do you think there's maybe advantages or disadvantages for designing legged robot vs like human robots, for example?
Yes, actually, we had a long history of discussion about this because we have an example like a bird. They're ostrich and many like a land, like a birds that doesn't fly, have a different morphology from seemingly human. But if you look at, this is a biology story. If you look at every single runners, their first proximal joint is actually pointing forward, which is kind of like a human knee. Like, somebody might say the birds are not. Actually, if you look at the birds, the first joint, which is a femur, is hidden in the body. And then, the knee equivalent is actually ankle. And same thing for the dogs. And if you look at the dogs, the cheetahs, felines, and canines, if you look at front leg looks like the opposite of the real leg, opposite of the human knee. It's actually not. There's a spatula, the scapula is actually moving quite a lot. Human scapula doesn't have as much range. Those animals use scapula a lot, and then that acts as a first joint sticking forward. So there's a clear dynamic advantage having a knee forward, the first joint from the body is sticking forward. But if your robot is not moving fast, if you really don't care about dynamic advantage, it's a debatable. It depends on what your task is. If you want to climb upstairs a lot, head forward, sticking knee forward is not going to be very useful. So knee backward robot will be much more convenient climbing upstairs all the time. But you have to think about climbing down. Is it easier? Probably not. So when it comes to just configuration spaces, geometry of your environment matters. But dynamically, the knee forward is always beneficial. That's why I believe humans and all these animals have a first joint from the body sticking forward.
And I also have a question here. What are the short and long-term technological roadblocks for your research and also for legged robot in general?
I think the challenges I talked about in the beginning is still going to be the roadblock. How can we write an algorithm that can handle so many discrete events? It's no longer continuous dynamics where gradients and a stochastic gradient works really well. It's going to be a lot of mixture of a hybrid dynamics. It's not just like hybrid dynamics between two phases. You have to deal with like 20 different phases, and then we have to choose from. And each phase has its own continuous dynamics, and we don't even know when to terminate that phase and so on. So the worst possible example is a grasping or any hand manipulation. Think about how many contact points. We don't even know how many contact points we're going to do given hand and given object. And when to make that contact and how to transition, it's going to just explode in your optimization space. So that's why I think we need to really think about high-level decision-making algorithm rather than just gradient-based or the quantity-based. I guess it's more like a state-based algorithm or phase-based algorithm. How to formulate that, how to generalize those approaches is going to be the biggest roadblock, in my opinion. Either you use a machine reinforcement learning or optimization based doesn't really matter. So that's sort of like my thinking.
Yeah, that's a good point. So we are closing to the end and have a few questions. The first one: why don't we have yet useful autonomous robots in real world, and how we can ensure what we develop is beneficial to humanity for designing robots?
Very, very important question. Again, I thought about this a lot. I attempt to start a company multiple times, and I closely watch over many other robot companies, and I review all this history of the robotics. I think there's a fine balance between the versatility of and the complexity, simplicity, I guess. And then good example is actually Roomba. Very good example is the vacuum machine, and it's extremely simple. And it's not just the company, because the company design is simple. The task is actually very simple. So that's where actually robot autonomous system can really shine. Many people ask when we're going to have a robot that can do laundry and cleaning dishes and cleaning the house and everything. And I ask, imagine somebody actually built that. How much is that going to be? And how complex is it going to be? And how about service fee and so on? And then I said, probably it's at least like $50,000. But if you think about all these vacuum cleaner, autonomous vacuum cleaner, laundry machine, dishwashers, of course, it's not as good as those multiple versatile robot, but all that combined to be at least at most like $3,000 compared to $50,000, maybe $100,000 robot. Then maybe it can do a little better than what we have. So you gotta be very careful with the all multi-purpose versatile machine that can do everything. Our cell phone did really well, but our cell phone doesn't have a single actuator. It's all digital, all IT technology. So my cell phone can be camera, recording device, like audio, web browser, like everything. Yes, this is versatile, great. But we carry around, we do all this physical behavior. When it comes to physical service, I'm still doubtful about having fully versatile, multi-purpose machine. Our successful machines are all one purpose. Our laundry machine has one motor instead of having 12-degree freedom hand with a 6-degree freedom arm to rub your laundry, using soap. It does everything with the one motor. Our dishwasher has a 2-motor, 1-motor. It's very simple and can do one thing really well. So going back to the Roomba example, Roomba has a few motors, but its task is very simple and limited, and is very fault tolerant, which is actually a very, very important aspect. Complexity goes hand in hand with the fault sensitivity, except the autonomous driving. When robot task is more complex, typically the task is a fault sensitive. You cannot make a mistake. If you drop a glass of the cup of glass every day, your robot is useless. When it comes to Roomba, you just always stick in the ground, and then maybe a vacuum, maybe bump into the wall a couple of times. It's fine. Nobody really care that vacuum machine make 100 mistakes in an hour. That's not even a mistake because it doesn't really affect much. But if your robot is doing something more complex, that typically lead to the very fault sensitive task. So this complexity and simplicity and versatility and specialized machine, we have to navigate in this space very carefully, while focusing on what value we provide as customers. So this is something the whole community need to really think about, and it's gonna evolve to something interesting. You have to really think about why Roomba is invented. Like Roomba is not even the first vacuum machine, autonomous vacuum machine. Electrolux has even older, more than 20 years of history, and yet there's no another autonomous robot that help us in our life. If you ignore like lawnmower machine and like swimming pool machine, those are kind of similar version of Roomba. There's those issues are not quite resolved yet. That's why there's still very few autonomous machine.
That's a very excellent answer, and thank you for the elaboration. I think that's really insightful as well. Yeah. And here's also a question about how we can enable more intellectually inclusive culture for competitive ideas. I don't know if we are thought about being intellectually inclusive in field of robotics in general. Do you think we have this kind of intellectual inclusiveness, or we have to work in that in terms of ideas?
There's also kind of tricky question, and then great question. Even in this world, we have this tension between countries, and how much can we share, and then and their countries are like doesn't respect like IP, for example, and we have to also work for the inclusion. Yeah, this is a lot more complex than I can just personally think of. But I'm a believer of I believe that like we should openly share everything to as much as possible to really move forward and make a progress. Because innovation not necessarily just happen because you're hiding something and you secretly develop something. If you look at Apple and if you look at Tesla, who actually benchmark Apple a lot, there's no like a secret like thing they do. They just work really hard to really focus on human value. Not necessarily they invent something completely out of blue. So I think the sharing idea is always, I believe, is always good.
Yeah, thanks for this honesty. Yeah, and do you think ego is important for the researcher?
I think so. Everybody has to make a peace with their ego, right? And but many cases the ego actually is a counterproductive. Somebody's care too much about their their name values or like like authorships, and so I think it's a fine balance. In academia, you cannot really work without acknowledging somebody's effort, but there's always challenge between like working with somebody at the same time make a peace with your ego and then your colleagues is a challenge. So this is another fine balance you have to deal with as an academic person.
Yeah. Yeah. And also, I have a question about what's your thoughts about publish or perish culture? Since you're doing very innovative research, how you manage between being innovative and taking risky ideas, and also the culture of publish and perish? I don't know if you have thought.
I think about that all the time, and I feel actually bad about myself and our group in a way that we care. We don't care publication as not as much as others. We care about what is really useful. We're extremely programmatic. That can be that can be bad for some of my grad students when they get a job. Their publication is not as good as others, and we don't publish as much as others. We in our group, we kind of our conviction is we decide to care programmatic solution rather than high citation or is it worth publishing? We have a lot of ideas. This could be good paper, but I don't think it's useful. Like we just don't do it. And I think it's very important to have. I wouldn't suggest to everybody because it's, as you said, if you don't publish, it's perish. So you have to balance. But if everybody's just search for the way to get published, I think community can go on a wrong direction. I can pinpoint a certain community, but some of the community happen to lock into that trajectory, and then it's less relevant as technology change, the world change, because they culture lock into that publish or perish, and then their publication is based on other publication is getting far away from real application. So that's something you got to be very, very careful.
Yeah, I think we need more like you, and that's actually what we need. We need more meaningful research and less publications. So I think you have to feel very good about that.
Yeah. I mean, the meaningful is a very multifaceted thing, and it's difficult to even quantify. Like academic, in my opinion, academic contribution is like, as long as it's helpful for other people's so research is useful. But if entire community is working on something not very practical, you got to think about it. But if you are working on something that shows something new and interesting, but what you publish doesn't really doesn't really give them enough ideas so that the other people can replicate or help, that's another challenge. I think this is something you have to balance. It's not necessarily one idea is better than the other.
Yeah. And here's a question: what are the most important quality you have gained while working in academia, or what you're doing? What is the most important qualities you have gained and you have to maintain?
I think the most important thing is still passion. I think passion also have many different stages, many different type of passion. For example, when we first designed a Cheetah robot, our passion was very extremely naive and pure. Like, we didn't care about anything else. We just want to make a machine that can do things like they've never done before. It's not wrong, but that kind of passion has a expiration date. Like, there are people like, trying to design a car that can go 1,000 miles per hour. It's admirable challenges, but has a short shelf life. Eventually, you had to grow and foster your passion into something more sustainable. That's where the other question, like, how can we make our research more useful to the humanity? That's actually a proper way to redirect your passion to really help the community and society, because eventually that's going to be the final source of motivation and final end route of your research. So it's not easy to develop something or work on something that's meaningful, because it takes a long time. So maybe one PhD student 5-6 years, which is okay. But if you want to achieve something really, really meaningful, it takes sometimes 10 years or 15 years. It's not easy to maintain your passion without having that really meaningful goal. So managing those passions, and you cannot give up what you like. You just intrinsically like something moving fast. I'm a big fan of moving fast and dynamic machines, so cannot give up that. But by that kind of pure passion by itself is not quite sustainable, in my opinion. So you have to latch into the ideas, or you have to evolve your dream to really, really help a real society, real people, help like elderly care, for example. Then you can maintain your passion, and then you can really fuel your research effort.
And lastly, what was the best advice was given to you, and was it life-changing?
Life-changing. That's very difficult.
Be very good advice. You keep in your mind, just.
I guess again, it is balance issue, but I think I still remember my brother said, like, somebody who work the hardest. I mean, somebody who enjoy what they do is gonna eventually prevail, because even though you're most talented in that area, if you're not really enjoying what you're doing, you can't really do that for a long time. Again, the sustainability issue. So I think I really constantly searching for what I like to do, what I can do at the same time. It can be useful for the society. So I start with what I like, but I start evolving toward how it can be helpful for the society, because otherwise people are not going to support you, and I don't want to do something that I'm really bad at. So that's probably the best advice I got.
Yeah, this is really a brilliant advice, and we have to do what we really enjoy, and people will feel it, of course. So do you have any final words the robotics community would like to say?
I really like our robotics community.
Yeah.
You just briefly talk about ego and stuff. I actually look other areas, and robotics communities are actually much more pure, less egocentric. I think we need to really tackle this versatility issue, the diversity issue. Our robotics are probably one of the most diverse community. All kinds of experts, all kinds of research is mixed. We have to really try to put our effort to how to integrate our effort, because the diversity is always challenging, and often great research is coming from one, like working on one small area. I think robotics are quite different. Robotics, we have to really integrate everybody's effort to really make a big difference. So I wish we can do more and more of the integration of diversity of our research in the future.
So yeah, thank you, Professor Kim. It was really enjoyable and insightful to have you on the podcast, and wishing from you more great work about legged robotics community. So thank you once again for your time. I really appreciate it. Thank you.
All right, thank you.
Thank you.